Now let's talk about jointly continuous random variables. Jointly continuous random variables. Remember when we talked about density functions for continuous random variables, and we said that the chance that this random variable takes on a value between a and b is just the integral of that function between a and b beneath the curve bounded by the x-axis, right? So it's just the probability that x takes on a value between a and b is just the integral from a to b f sub x of x dx, right? Good. Well, what if we had two random variables? Let's think more like this. Let's think like here's one of my random variables, x runs along that way. But then I've got this other random variable, y, just like in the discrete case, okay? Except that they're continuous. So maybe I could describe their joint behavior with some kind of a joint density function, right? See? Something like that. Something like this, maybe. Now what does it mean to talk about probabilities? Well, see, now if I want to know the chance that this random variable, say, takes on a value, say, down here in this region, say, in this region A, call it A, then it's just, instead of it's sort of the same thing, right? It's just sort of going to be the area of the curve bounded between this. It's going to be the area bounded between this density curve and A. But really, though, it's not area; it's volume, right? It's volume. So we can accomplish this. We can get this volume by doing something called taking a double integral. Okay, by taking a double integral. So we'll say that x and y are jointly continuous. Jointly continuous random variables if there exists a non-negative function and we'll call it, say, f sub xy such that the joint CDF can be expressed like this. It's this so-called double integral, and we'll talk about what that means in a minute for those of you who haven't seen double integrals. It's this is defined to be the probability that x is less or equal to little x and y is less or equal to little y. Of course, that's what the joint CDF always means. This will be the integral from negative infinity up to x, and then integral negative infinity up to y of this joint density function. Maybe I'll use variables s and t here, and I want dt and then ds. Okay, and this is for all x and y in the reals. Okay, now call it double integral because there are two integral signs. There are two integrals to be done. The first one is this one right here. Okay? When we write dt, ds like this, this d whatever goes along with this integral. So it's like we're just going to do this integral, and then we'll do the next one. Okay? And that gets us volume. That gets us the volume that's bounded by this curve and the plane there over this region. It's region A. Okay, or specifically, you know, this would be the probability that, say, if this is A1 and A2, and this is B1 and B2, then you could say the probability that X takes on a value between A1 and A2, and Y takes on a value between B1 and B2 would be the integral from A1 to A2, integral B1 to B2 of the joint density of these two guys. Okay, dt ds, like that. Okay, or again, we do this integral first. All right. By the way, this function right here is called the joint probability density function. Joint probability density function, or joint PDF, or just PDF. Okay? And again, so it sort of looks like a bed sheet or something that's resting over, flying over a plane there. The total area beneath this, or the total volume beneath this bed sheet should be 100%.